Space is not as empty as it seems. Objects of all sizes orbit the sun and sometimes pass close to the Earth. Are these near-Earth objects a hazard to people, to property, to national security? Are our space-based telecommunications, navigation, and surveillance systems vulnerable? Scientists at Sandia National Laboratories are developing impact models to help provide answers to these questions. Our atmosphere protects us from the smallest particles, which we see as meteors when they burn up at high altitude. Occasionally, larger meteoroids collide with the Earth's atmosphere, putting on spectacular aerial displays. Rarely are they large enough to reach the ground or cause any damage, but they remind us that our planet is constantly being bombarded. Collisions with asteroids are far less frequent. The Earth is struck by projectiles greater than 30 meters in diameter only once every 100 years or so. The last time was in 1908. It happened in an uninhabited forest in Siberia, near the Tunguska River. To witnesses hundreds of kilometers away, the world seemed to be coming to an end when a huge mass of fire descended from the sky and exploded with a deafening roar. The resulting shockwave ravaged the countryside, blowing down trees up to 30 kilometers away. Debris from the blast brightened the skies above much of Europe and Asia for several nights, as far away as England and Denmark. The cloud of dust was so high in the atmosphere that direct sunlight illuminated it all night long. When a scientific expedition arrived at the site many years later, researchers were unable to find the impact crater they expected. The pattern of fallen trees demonstrated that the projectile exploded before it could hit the ground, and only traces of the meteorite were ever found. Much of our understanding of how objects explode in the atmosphere and our assessment of the hazard from these events comes from Tunguska. Scientists developed models, but without the chance to actually observe an impact, there was no way to make sure they were correct. A breakthrough occurred in the summer of 1994, when more than a dozen large fragments of comet Shoemaker-Levy 9 plunged, one by one, into Jupiter's atmosphere. Scientists had an unprecedented opportunity to test their impact theories and to learn firsthand what happens when a celestial object explodes in a planet's atmosphere. As impact specialists predicted, giant fireballs, or high-velocity plumes of hot gas, were ejected thousands of kilometers into space, where they cooled, condensed, and fell back. The debris from these collapsed plumes formed clouds of particles high in Jupiter's atmosphere that reflected direct sunlight, even when they were on Jupiter's night side. Scientists at Sandia are now investigating the possibility that the Tunguska explosion ejected a fireball like the ones observed on Jupiter, and that the bright night skies across Europe and Asia were from its collapse. New simulations make sense out of the stories some eyewitnesses at Tunguska told of a tongue of flame that split the sky in two. If satellites had existed in 1908, would this tongue of flame have risen high enough to destroy them? Less than a century after Tunguska, we've become dependent on our satellites for communications, navigation, surveillance, and military operations. As we put more satellites into lower orbits, these technologies will become increasingly vulnerable to impacts. Just as planners assess the risk from 100-year floods and 100-year earthquakes, Sandia scientists are now calculating the consequences of 100-year impact events on Earth using the knowledge gained from Shoemaker-Levy 9. For example, they compared their simulations of the Jupiter collision to an eyewitness's painting of another Siberian impact, the 1947 Sikhote-Alin event, and discovered distinct similarities. What if a 100-year impact occurred today? If it happened over a population center, it would have devastating consequences on the ground. But most of the world's surface is sparsely populated, so the odds are that it would be a long way from the nearest city. matter where the impact occurred, simulations suggest that the fireball would rise into the path of orbiting satellites. As a direct result of their impact and shock physics research, Sandia scientists have identified a new hazard to satellites and space operations. By comparing their simulations of the Jupiter impact to actual observations, they can now use validated models to help determine how seriously this hazard should be taken and what to expect from the next 100-year impact on Earth.